All right, welcome to lecture. We'll get started in just a few minutes or so. Again, we're continuing on here in chapter 9 and acid and bases. So I think this is about where we left off. So again, we'll get started in a minute. As usual, if you have any questions, feel free to type them in the box, and obviously we'll get your questions answered as we go through. And again, we'll get started here in just a minute or so. All right, so last time we were talking about acid and bases, and remember that basically a acid is something that's able to produce H plus in solution, while a base is able to produce hydroxide, OH minus, in the solution. And remember that when we're talking about basically acid and bases, that when we deal with H plus and H3O plus, which is also what is known as the hydronium ion, they're essentially the same. So they're used interchangeably. So sometimes you'll see people use H plus in formulas. Sometimes you'll see people use H3O plus. But again, they're basically the same here in acid and base chemistry, both in formulas and also in equations. You'll see them sort of interchange. I personally, like I said, I think last time we'll use H plus a lot. So anywhere I use H plus, you can use H3O plus, which is the hydronium ion, and it basically will be the same thing. It basically means the acid part of a solution, while when you typically see OH minus, which is hydroxide, it represents obviously the base part of the solution. So what we left off with here is talking a little bit about acid and bases and some of the basic definitions of them, and that's really sort of the true basic definitions here of acid and base is really that ability to produce that H plus, H plus and OH minus. And when we're talking about producing it, we mean basically free ions floating around in the solution. So the presence of those free ions floating around the solution, and as we'll talk about today, depending on sort of the amount of either the H plus in the solution or the amount of OH minus in the solution, we will determine whether or not the solution perhaps is acidic or basic. So for example, when we make something like hydrochloric acid, is you can take hydrogen gas and dissolve it in water. And when it does dissolve in water, it will basically break apart into these ions. And there's our H plus that's being formed. And again, that would be hydrochloric acid. Remember that something like hydrochloric acid is a strong acid, which means basically it's a strong electrolyte. So when it's in solution, it will be 100% broken apart. And you basically will have all H plus and all Cl minus floating in that solution. You wouldn't have any more of the HCl units still together. While when we look at the sodium hydroxide, it's a strong base. Again, it's going to be a base because it's able to produce here OH minus in solution. And that free OH minus in solution is going to make it a base. And same thing, because it's a strong base here as our strong acid, it will be 100% the sodium ions and the hydroxide ions floating around in that particular solution. So we sort of talked about that early definition of acid and basis, the Arrhenius definition, and that again was something that was able to produce H plus in solution and something able to produce hydroxide OH minus in solution. And again, he did a lot of work and it was a good step forward in terms of acid base chemistry, but it was a little bit limited in terms of it oftentimes focused in on bases that actually had hydroxide in it, like OH minus. So something like sodium hydroxide, potassium hydroxide, and obviously these have OH minuses in them. And again, not all bases will necessarily have OH minus in it. So a good example of that is NH3. That's ammonia, and that's actually a weak base. And although it does not have an OH minus in the actual formula, when it does react with water, as we'll see here in I think just a second, but just to give you a preview. For example, when NH3 reacts with water, it will make NH4 plus, and there's our OH minus that's going to be produced in this case, again, making it a base here. And as we'll talk about a little bit in this chapter as well, it's considered a weak base because although it can still produce hydroxide, OH minus, which is sort of your definition of a base, it does need to do sort of a reaction first. It needs to react with some water there to actually produce the hydroxide, as opposed to something like sodium hydroxide, which, as we will see and sort of talked about a little bit last time as well, it pretty much just needs to go for a swim there in water. And once it's in water, it's going to 100% just break apart into those ions. So a more sort of general definition of acid and bases sort of came about, and that is one put forth by Brønsted-Lowry. And the Brønsted-Lowry definition of an acid and base deals with the idea of protons. And remember that another sort of terminology is a proton is an H plus. Yeah. So again, definitely an acid base chemistry. The H plus is referred to as a proton. And an acid is basically a proton donor, which basically means that it will give away an H plus. So an acid will donate, as it says there on the bottom, an H plus, while a base will be the one that will actually accept an H plus. And a couple of things about this is really important in terms of understanding the acid and base sort of definition here is sometimes people oftentimes will focus in on just the H part of it, but the plus is important as well. So that plus will actually change the charge of things as they either donate the H plus or if somebody accepts the H plus. So you got to keep in mind that it's not just necessarily an H is going to be sort of donated and accepted. You will have that sort of positive charge, which will have an effect on the overall charge of molecules as they're accepting and donating those H pluses. So if we look at sort of a Brønsted-Lowry sort of reaction here, and this is just a generic sort of reaction that's done for HA is a generic formula for an acid. Remember, really what makes something an acid is it has H plus and some type of negative anion, which is basically what that represents. So for example, something like HCl, which is hydrochloric acid, it's H plus and Cl minus. The Cl minus would be the A minus here in this generic formula. So we have our acid, and in this particular case, the water is actually acting as the base. And what we're going to have is basically our acid here donating the H plus over to the water, which is acting as the base. It's going to accept the H plus. And when it does on the other side, the water becomes H3O plus, and the HA, which is our acid, which has given away its H plus, will become the A minus. And the consequence here of sort of the Brønsted-Lowry definition of acid and bases is we gain partners. And the acid on this side, its partner on the other side would be over here where the A minus is. And its acid, its partner on the other side becomes what's known as the conjugate base. While the base in this case, which is the water, its partner on the other side here will be the H3O plus. And it's a base on the left-hand side of the arrow, and its partner on the other side would be the conjugate acid. So the definition of Brønsted-Lowry bases will make these sort of pairs, and a couple of things about sort of acids and bases and conjugate acid and bases. The just straight old acid and bases usually are always found on the left-hand side of the arrow, so that's your reactant side, while your conjugate acid and bases are typically always found on the product side, which is obviously where we have our H3O plus in this case and our A minus. The other really important thing in terms of that relationship between, say, an acid and its conjugate base or a base and its conjugate acid is the difference between those two things. And it really comes down to the definition of an acid and a base. And that definition is it will donate or accept an H plus. And basically what that means is there is only one H plus difference. So when we go from our acid to our conjugate base, it's one less H plus. While when we go from our base to our conjugate acid, it's one more H plus. And that's a really important sort of distinction, is that idea of just one H plus difference. So in order for things to really be a sort of acid conjugate base pair or a base conjugate acid pair, the only difference that you could have between those two things is just that one H plus. Again, if you have more than one H plus difference or other elements involved that are different between the things, then they are not really related to each other. They're not really partners. It can only be that one H plus difference. Any questions on that? Now, here's a couple of examples like we saw before there. There's our generic formula there, our HA plus our water. Again, just like we saw in the last slide, our HA is our acid. HA, again, is an acid, which is sometimes referred to as a monoprotic acid. And basically what that means is it has one H plus to donate, basically, or give away. You can also see things like H2A. That's a generic one for what is referred to as a diprotic acid. And that means that it has actually, as you can see here, two H pluses to give away. And sometimes you'll see H3A kind of used as a generic formula, and that is what is referred to as a triprotic acid. It has, as you can see here, three H pluses to give away. So you'll sometimes see these generic formulas used in acid-base chemistry. And again, they're just really representations of real acids, but more of a generic formula. So as we talked about before, for example, this HA could be like HCl, which is hydrochloric acid, for example. H2A could be something like H2SO4, it would be sulfuric acid. H3A could be something like H3PO4, which would be phosphoric acid. So again, you'll sometimes see these generic sort of formulas used when people talk about acids and bases. Now, when we look at the bottom there, there's our hydrochloric acid, which is basically just breaking apart in water, basically. And again, here in the actual equation, we have water in it, and that's how we produce that H3O plus. But in the same case here, the hydrochloric acid is probably obviously acting as our acid, while again here water is acting as our base. So the H plus is heading over to the water. And again, that's going to produce H3O plus and Cl minus. The H3O plus going to be the conjugate acid, as you can see there, to the base, which is water, while our Cl minus will be our conjugate base to our acid, which is the hydrochloric acid. And again, if you look at the difference between those two things, the only difference is one H plus. So the difference between HCl and Cl minus, one H plus. The difference between water and H3O plus is also one H plus. And again, that's extremely important in terms of the only difference that we see is those one H plus difference between them. And again, as you can see, regular old acid and bases found here on the left-hand side of the arrow, all your conjugate guys, acid and bases found on the right-hand side of the arrow. And that is typically how it always is when you look at these things. And here's just sort of the Lewis structures, sort of showing you what's going on here. Again, our HCl is going to break off that H plus, is going to donate over to the water, and it's going to make H3O plus, while our HCl here will make the Cl minus. producing our hydronium ion. So why don't you take a second or two here and basically look at each of these and determine whether or not these guys are conjugate acid-base pairs. So when you're looking at these guys, what you're looking for is, are these guys related to each other? And again, the important thing is, are they related to each other by just that difference of one H plus? So take a minute here and then we'll talk about it. Okay, so let's take a look. So again, the idea here when you're trying to determine whether or not something is a pair, a partner, sort of conjugate acid base, what you're looking for really is that H plus. And again, it just needs to be that difference of just one H plus. So when we look at the first one here, between HClO4 and ClO4 minus, what we do see is the only difference between those two is an 1H plus. So these guys would be a pair. And again, you can see it however you want to kind of look at it. If you want to take this ClO4 minus and you basically put the H plus on it, that's going to give you HClO4, which is obviously over here what we started with. Or alternatively, you could just take the H plus off and you'll end up with the ClO4 minus. HCl and ClO minus, there is a difference of 1H plus, but in this particular case, these are not going to be pairs, as this guy here has an O, an oxygen, no oxygen found here. So these guys would not be a pair. Again, although there is a 1H plus difference, there's also a difference of more than just the H plus. So we have a difference of oxygen here as well. So that again is not going to allow them to be pairs. H2PO4 minus and HPO4 2 minus, these guys are pairs. The only difference is 1H plus. And again here, if you look at H2PO4 minus and you take off the H plus, so taking off the H plus is going to get rid of one of those hydrogens, leaving us with HPO4. And now this is what I was talking about earlier. The plus is important. When you take off the plus, you become one more negative, and that's how we get to basically -2 there. So important to remember that again, that plus is kind of changing as well, going to affect the charge as you go again from one to the next. But this isn't a pair, as the only difference is that H plus. And lastly here, our nitric acid and our nitrate is also an H plus. Again, the only difference is we take off the H, and here it's neutral. So when we lose that positive, we become one more negative, and that's how we get to the -1 here. So it looks like everybody is a pair except number 2, not a pair. Any questions on those examples there? All right, so why don't you take a minute here, and what we're looking for is to write the conjugate base for each of these. So write the formula for the conjugate base to each of these following guys. So take a minute here, make sure you can get them correctly, and then we'll talk about it. Okay, so let us take a look here and see. So our conjugate base for each of the following. So sometimes when you're asked this type of question to write either the conjugate base or the conjugate acid, what you kind of want to think about is sort of the relationship of those things. So if you remember that our equation, it was our acid plus our base gives us our conjugate acid plus our conjugate base. And again, the relationship is the acid on the left-hand side is related to the conjugate base on the right-hand side, while the base on the left-hand side is related to our conjugate acid on the right-hand side. So in this particular case, we're looking for conjugate bases. And that means that what we are starting with is actually an acid. So you could basically go by the definition of an acid, and that is H plus, right? And that is going to be somebody that's going to donate an H plus. So sometimes it's helpful for what am I looking at? H2 against neutral charge, and that is for first. We're going to treat it as H with S. Now we're here, and again use the and to lose just the plus or H2 minus. Here we have anything else changing, and we're going to make sure the key should you basically take it off. And the key is nothing else changes other than the H, except for perhaps the charge will change, obviously, as you're doing that. Any questions on any of those sort of examples there? Why don't you try this one here? Let's say we started with HCO3 minus. Why don't you write the conjugate acid for it? And why don't you also write the conjugate base for it? So take a moment here and write both formulas. So starting with HCO3 minus in each case, write either the conjugate acid for it, and then write the conjugate base. So take a moment here and see what you come up with. Okay, so let's take a look. So in this case, if we start with HCO3 minus, and we want the conjugate acid. So again, we can kind of think backwards. If I'm looking to draw my or write my conjugate acid, that means in this particular case, the HCO3 minus is actually going to be a base. And definition of a base is something that will accept an H plus. So here we're actually going to accept an H plus. So that means in this case, we're actually going to put it on. So it would be H2CO3 would be the conjugate acid in this case for bicarbonate there, HCO3 minus. Now, if we're doing our conjugate base, just like we saw before, conjugate base, the original guy is an acid. That means in this case, he would act as an acid, and we would take off the H plus, and we would end up with CO3 2 minus. Now, in this case, you may be looking to go, can it be both things? And actually it can. So in this particular case, going this way, this guy is acting as a base, while going to the right there, he's acting as an acid. And things that have the ability to act as both an acid or a base, those are things that are referred to as being amphoteric. So an amphoteric substance is basically a substance that has the ability to act both, again, as an acid or base. And things typically with a hydrogen, like we see here in bicarbonate, and like a minus charge, they typically do have sort of that ability to kind of go both ways. In certain cases, they could act as an acid. In other cases, they can act as a base. Water as well. It doesn't have a charge or anything like that, but water also, as we will see and have seen a little bit, can act as an acid or a base as well. So amphoteric means, again, just that something has the ability to act as an acid or base. Any questions on acid conjugate base pairs or how to write them? Obviously, you do need to be able to identify what's an acid. You need to be able to identify what is a base, and obviously what's a conjugate acid and base. And obviously, if you're given either an acid or a base, be able to write the conjugate acid or conjugate base for those guys. Any questions on any of those? Okay, so let's talk a little bit about acid strength. So the forward reaction of an acid and water, remember that the generic sort of reaction occurs when we react an acid and a base together, for example. We typically will get our acid plus our base. We'll make water and a salt. Remember, a salt is just an ionic compound. And really the water part, which is H2O, usually comes from the H plus from the acid, and a lot of times the OH minus from the base. And again, that's typically how we get our sort of water to come together. And in certain cases, the products, that salt and water, can kind of combine and come backwards. And we usually get this situation here where we get these arrows heading in both directions. So as we've talked about, this is again a reversible reaction. And we saw that kind of with weak electrolytes. And that means, again, it has a forward direction heading from reactants to products, and heading the opposite way, it has a reverse direction heading from products back to reactants. So at some point, the products will be there in enough sort of concentration to have that reverse reaction start to happen. And that basically representation there gives us sort of the differences between our sort of strong acids and weak acids, or strong bases and our weak bases, is whether or not it's sort of a one-way street, if you will, everybody heading to the products, or if it's sort of a reversible reaction where everybody's sort of heading really towards the reactants or staying to the reactant side. So if we have the forward reaction that really predominates, maybe not such a giant arrow here, that's basically a strong acid situation. And usually something, for example, like hydrochloric acid is a strong acid. Again, pretty much everybody is heading to the product side, and 100% of what you got in that solution is those ions there, so that H plus and Cl minus. So you won't have any of the HCl units still together in solution, and basically you'll have just those ions floating around. What that essentially means is that HCl was able to produce pretty much a lot of these guys. Yeah, so a lot of free H pluses were able to be produced by it, and that's why, again, it's considered a strong acid. And that's what it means when it talks about it being completely ionized or completely dissociated. Those are fancy words for it. Basically 100% broke apart into ions. You have nothing but pretty much ions in that solution. Now, if the opposite is sort of true, where again the reaction is really heading in the reverse reaction, you typically will see, unlike up on top here, this sort of one-way arrow, you will see the arrows heading in both directions. So this is, again, a situation where you'll see those arrows going in both directions, and that is definitely an indication of a weak acid. And basically what that means is this is really a weak electrolyte. So really something like a strong acid or a strong base is a strong electrolyte, which, as we talked about, 100% breaks apart. And something that's a weak acid or a weak base is basically a weak electrolyte. And basically what that means is it pretty much stays together, but will produce a little ions. So since it produces a little bit of ions in solution, it's still able to break apart and still able, for example, to produce some H plus. So an example of a weak acid is something like, for example, here, hydrofluoric acid, HF. Again, you see those reversible arrows. It will break apart into H plus and F minus. But mainly in solution, this is what you have, is basically those guys still together. But it's able to produce a little bit of these guys. And again, it meets that definition of an acid because it's still able to produce some H plus in solution, which is kind of, again, your definition of an acid. But it's going to produce nowhere near the extent, for example, of HCl. When hydrochloric acid goes into solution, again, 100% of it's going to break apart, going to produce a lot of H pluses very, very quickly, and obviously make that solution probably pretty acidic. And that's why, again, it's a strong acid. HF also, when it goes for a swim, basically going to stay together. So you'll have a lot of the HF molecules still together. And because they're still together, the importance of that is we're not producing as much free H plus. And that is the key for sort of something being sort of a strong acid, weak acid is, you know, the amount, if you will, of H plus is producing. But still technically able to produce something, some H pluses, so still technically, you know, an acid, but going to be a much weaker acid in something like hydrochloric acid. And a couple of important sort of relationships that we see in terms of our acids and conjugate bases and our bases and conjugate acids. Again, the relationship when we look at sort of the strength between an acid plus a base in this reaction, right, going to give us our conjugate acid and our conjugate base. And the relationship between, say, an acid and its conjugate base, or a base and its conjugate acid, the relationship is sort of an opposite relationship. And I guess what I mean by that is if it starts out as a strong acid, its partner on the other side, its conjugate base, will be relatively weak. And vice versa, if it starts out as a weak acid, its conjugate base will be relatively strong. Same thing with the base. If it's a strong base on the left-hand side, its partner, the conjugate acid, will be relatively weak. And if it's a weak base on the left-hand side, its partner, the conjugate acid on the right-hand side, will be relatively strong. So what we mean by that, again, if we just kind of look at what we're looking at here, HCl is the acid, its conjugate base is Cl minus. And in this particular case, HCl, again, is a strong acid, which means the Cl minus is relatively weak. What that means is a little bit outside sort of the scope of this class, but what that essentially means is the Cl minus won't continue to react. So in certain cases, the partner, the conjugate acid or the conjugate base, will continue to react in solution. So it will react with water and produce actually more H plus or OH minus. So what's known as hydrolysis. We don't really get into that in this class, but it has the ability basically to sort of continue to react. Now, if you look at something like HF, that is our acid. Get over there. There you go, HF. And its conjugate base is the F minus. And in that relationship, HF is a weak acid, which means the F minus is actually a relatively strong conjugate base. And again, what that means is it's not a strong base like sodium hydroxide strong or potassium hydroxide strong. But essentially what that means is it has the ability to continue to react. So if you put HF in solution and you produce some F minus, the F minus itself has the ability to basically to react with water, and it will react with water actually and produce more hydroxide in that particular solution. And so it does have the ability to continue to react. So in terms of the relationships between acid and bases and their partners, again, it's sort of an opposite relationship in terms of strength. If it comes from something that's strong, the conjugate partner will be relatively weak. If it comes from something that's weak, the conjugate partner will be relatively strong. Now, there's some strong acids there. H2SO4 is considered a strong acid. Hydrochloric acid is a strong acid. Nitric acid is a strong acid. Perchloric acid is also another strong acid. Some other strong acids, again, HBr is a strong acid. HI, which is hydroiodic acid, is also a strong acid. So there's like 6 kind of strong acids. We talked a little bit about strong bases before. Again, things like sodium hydroxide, potassium hydroxide, as we might have talked about, I think last time as well, pretty much group 1 and 2 on the periodic table that contains hydroxide. A lot of them are strong bases, not 100% of them, but a good amount of them are. Kind of if you start where sodium is on the periodic table, come down, go to the next group, and then down. All those guys with sort of hydroxide attached to them, like calcium hydroxide and all those kind of things, usually will represent sort of strong bases. Some weak acids, just to give you some of those. HF, which we talked about, is hydrofluoric acid. Acetic acid, which is basically the main part of vinegar, is also a weak acid. HNO2, which is nitrous acid, is a weak acid. So these are some examples of some weak acids. Weak base, something like NH3 is a weak base. And that's probably a pretty common weak base that you come across, which is ammonia, is pretty common sort of weak base. Now, something like sulfuric acid is a diprotic acid. And again, as we talked about a little bit earlier with those sort of generic formulas, a diprotic acid means it basically has 2 H pluses that can come off. Something that's a triprotic acid will have 3 H pluses come off. And a monoprotic acid will actually have, again, 1 H plus that can come off. Now, just to illustrate sort of how these H pluses come off is they actually do come off one at a time. So they don't typically, I'll spit that out, right? Typically, both just drop off right at once. So for example, if we took something like our H2SO4, which is a sulfuric acid, the first thing that will happen is really the H2SO4 will lose that first H plus. So it'll drop off an H plus, and you'll be left with HSO4 minus. And then the next thing that happens is that HSO4 minus will lose the second H plus and make sulfate. And again, a couple of things about this. As you could probably imagine, it's much easier to pop off that first H plus. Once you do pop off that first H plus, it gets extremely harder to take off the second H plus. Again, what happens obviously as you pop off that first H plus, you're taking it off for something that is neutral. When you take off the second H plus, you're now taking it off for something that is negatively charged, and you're trying to remove something that's positively charged. So it's going to be held a lot tighter in that particular case. And the second thing that you get basically is sort of the reaction we sort of think about. If we add both of these reactions together, what will essentially happen is everything on the left-hand side will stay on the left-hand side. Everything on the right-hand side will stay on the right-hand side. And we'll end up with something like this. And again, all I did is basically everything on the left stays on the left of the arrow, everything on the right stays on the right. And things that are the same on opposite sides of the arrow will cancel out or reduce. It's kind of like in math when you have an equal sign and x's and move it to the next side, kind of subtract it. And what that leaves you is the reaction that most people think about or sort of think happens here, and why people think it sort of happens all at once. This is really the overall reaction that's taking place is it will lose 2 H pluses and be left with your sulfate. This is also why when we look at what happens really sort of individually here, this is why when we talk about acid and conjugate base pairs, this is why if we look at this guy and this guy, although they are sort of related to each other, they are not pairs because again, the difference here is 2 H pluses. And that is why when we look at the H2SO4 and the HSO4 minus, these guys are pairs. Yeah. And also while the HSO4 minus and the SO4 2 minus are also a pair. And again, the difference between those two things, just one H plus difference in each of those. But as we go from H2SO4 to SO4 2 minus, that's actually two H pluses, and they're not pairs because of that. And really the reason is, as you see on the left there, the H pluses, although sometimes we look at the overall reaction where we see the two H pluses basically drop off, it actually does happen in what's referred to as sort of a stepwise fashion. And really it's a sort of two-step process. And that's why, again, the H2SO4 and the HSO4 minus are pairs, and the HSO4 minus and the SO4 2 minus are pairs. But going directly from H2SO4 to SO4 2 minus, they're not pairs, because really it doesn't sort of happen that way. It happens more in a stepwise fashion. Any questions on that there? Okay. Maybe. Let's see here. There you go. Something's going to come up. All right. So let's talk a little bit about water. Water, again, is an amphoteric substance. And as I mentioned earlier, basically an amphoteric substance is a substance that can act either as a acid or a base. So depending on sort of the situation as to sort of which one it will do. And there's sort of other factors that, again, in this particular class, we don't get too involved in. That will help you decide whether or not, it will act as an acid in this case or a base in this case. But something like water does have that ability. So in our first reaction here with our NH3, the water is acting as an acid. So in this particular one here, the H plus is going to be transferred over to the NH3 and making NH3 becomes, which is our base, NH4 plus becomes our conjugate acid, while water, again, is our acid, and the OH minus in this case will be the conjugate base. This is the sort of a basic solution when you do this. Although water is acting as an acid, this is going to be a basic solution because we are producing hydroxide. So that's a key thing to remember as well as we get through the rest of this chapter when we talk about sort of acid and bases. If on the product side you see OH minus, probably going to be a basic solution overall. If on the product side you see H3O plus or H plus, is going to be an acid. And here in this case, the water is acting as a base and the HCl is acting as the acid. So it's going to donate the H plus over. And again, that's going to give us our conjugate acid here and our conjugate base. And again, here we see H3O plus being produced. And that's going to tell us this is probably going to be an acidic solution. Now, water is kind of crazy. It could even react with itself, which is essentially what happens when you have sort of a water solution. So one water acts as an acid, one acts as a base. So, in this particular here, say the first guy is our acid, this guy is going to act as the base. So in this particular case, the water is going to move the H plus over, and we will produce H3O plus and OH minus in this case. Now, the process where that sort of occurs creates an important relationship when we talk about acids and bases, and it creates sort of a weak electrolyte sort of system. And basically what that means is we get this reversible reaction where we have basically H2O going to H plus and OH minus. And in a reversible reaction, we can write a relationship of those guys, which is known really as an equilibrium constant, which is K. In this case, is what's known as KW for water, basically, is what the W stands for. And that is the concentration of H plus times the concentration of OH minus will equal this value of 1 times 10 to the minus 14. Now, that's a constant, and it is constant, technically speaking, for 25 degrees Celsius. And probably in this class and most classes that you take, if you ever need to use this value of KW, the 1 times 10 to the minus 14 is probably going to be the right number. But it is an equilibrium sort of constant, and it does really change with temperature. So If you're not doing 25 degrees, it might be a slightly different number. But again, in this class, and probably even 1A if you take it, you're probably not going to come across too many times it's a different number. So usually you almost can think about 1 times 10 to the minus 14 as sort of always being the right number. But the truthful answer is it may not always technically be the right number, but probably 99.9 times you use it, it will be the right number. And we can use those things. And when we see these little brackets, by the way, when we see this sort of bracket, it does mean concentration. If I could spell there, concentration, there we go. And basically what we're talking about is molarity, which is moles per liter. So when you see those little brackets around something, it does mean concentration, and usually molarity is what we're talking about here. Now, again, in this formula, this is probably how I'll write it most of the time, but you can write it KW equals H3O plus OH minus equals 1 times 10 to the minus 14. So again, the H plus, H3O plus, as I mentioned before, you'll see it used sort of interchangeably in both formulas and also reactions or equations. And again here, H plus, H3O plus, same deal. Now, the relationship between H plus and OH minus is an important one to understand as well. And it's basically an inverse relationship. So basically, as the concentration of H plus increases, the concentration of OH minus will decrease, and vice versa. As H plus goes down, OH minus will go up. So basically, as one goes up, one goes down, and vice versa. So they are sort of tied together, and one has an effect on the other in terms of being in the solution. And really what we're measuring here, if you will, is those free H pluses and the free OH minuses that we find in the solution. And the concentration of those things will allow us to really determine whether or not this thing is acidic, basic, or neutral type solution. And we can use these concentrations and make that determination. So if we use sort of that equation there, and if you needed to use it, this is basically how you would rearrange it in each of these cases. And if you were given the OH minus concentration like you would do on the left-hand side there, you would take 1 times 10 to the minus 14, which is the value of KW, and you would divide it by OH minus concentration. Or vice versa, if you're given the H plus concentration and you want the OH minus concentration, you take 1 times 10 to the minus 14 and divide it by the H plus concentration. The good news is it's really the same calculation regardless of which one they give you. You're basically just going to simply take 1 times 10 to the minus 14 and divide it by the concentration they give you. Super important here, and definitely in this chapter, if you've forgotten your calculator or those important buttons, this is definitely for sure the chapter where you want to make sure that you punch things in scientific notation correctly. So again, you want to make sure that you use your exponent button, because if you do not use your exponent button, definitely in this chapter, especially a little bit later on when we start talking about logs and stuff like that, you will find yourself with the wrong answer. What you'll typically see is like the front part of the number looks pretty good, and then you get to the times 10 part and you're like, oh, it's supposed to be -8, but I got like -9. Like off a little bit, and that usually means that you're not punching these things in correctly in your calculator. So a reminder that if we were going to do the 1 times 10 to the minus 14, we would put 1 in our calculator. On a lot of people's calculators, you hit the exponent button. Again, that would pop the 1 in the E, or it may pop the 1 in a couple of zeros, and that exponent button represents the times 10 part of the number. So that's basically what that means. And then you would hit the negative button, not the subtract button, and 14. So again, it would put something like that, and this guy would become something like this probably. So you definitely want to make sure you're using your exponent button in this chapter for sure. Otherwise, you will be off by a lot of sort of calculations. Now, you can use those concentrations to determine whether or not a solution is acidic, basic, or neutral. And again, the idea here really is, if you sort of think about it, the H plus is really the acid part of the solution. The OH minus is the base part of the solution. So if you calculate it and the H plus is larger than the OH minus concentration, basically the acid part is larger than the base part, it will be acidic, as you see there. If you calculate and the H plus concentration is less than the OH minus concentration, it would be basic, as the base part is larger than the acidic part. And if you calculate it and the H plus equals the OH minus, and what that means is they both will have a value of 1 times 10 to the minus 7. So that's an important thing as well. They both would have the exact same concentration if it's neutral, and it would be 1 times 10 to the minus 7 in this particular case. Any questions on that? All right, so you got a few here. So there's 4 different ones here. So for each of them, calculate either the H plus or the OH minus, depending on which one they're given, and then determine, is the solution acidic, basic, or neutral? So take a minute or two, and then we'll talk about it. All right, so let's take a look here and see how we're doing. So in each of these cases, we're given either the H plus or the OH minus concentration. And again, really here, we're using our KW relationship, which is the H plus times the OH minus equals out 1 times 10 to the minus 14. And really the same calculation, no matter which one they give you, you're basically just going to take 1 times 10 to the minus 14 and divided by what they give you. So if we look at the first one, we're going to be looking for the OH minus concentration. And we're going to take 1 times 10 to the minus 14, and we're going to divide it by the 3.4 times 10 to the minus 4. Again, we want to make sure we use our exponent button. And if we do that, it looks like we end up with a concentration of 2.9 times 10 to the minus 11. And a couple of things about this answer, since it is a concentration, we do want to put molarity here, since our original unit over here was molarity. And that would be our answer. Now, to determine whether it's acidic, basic, or neutral, we want to look at the OH minus concentration, which is really the base part of the solution, and want to compare it to the H plus concentration, which is the acid part. And you want to see which one is larger. And if you look at these numbers and you compare these numbers, you will find that the H plus in this case is larger than the OH minus. So sometimes people have a little trouble with that aspect of it, and it has to do with the exponents. So when we compare a number that's the H plus concentration here times 10 to the minus 4 versus a number that is times 10 to the minus 11, even though 11 is larger than 4, the negative is really important here, because the negative means when we take the 3.4, we're going only 4 places this way. But when we take the 2.9, we're going, I won't draw it all, but we're going, I'll go 11 places to the left. And we're obviously putting zeros right there in front of all those things. So the negative 11 is actually a much smaller number than to the negative 4. And basically what that means is the H plus concentration is larger, and the first guy here would be acidic. Any questions on that? By the way, when you're asked that question in this chapter, is a solution acidic, basic, or neutral? There is really only one answer for that. It's either acidic, basic, or neutral. Not so much happens that with that question here, but later on, sometimes people have a tendency to give multiple answers. So they'll go, this solution's acidic, while at the same time it's basic as well. So again, only one answer for that: acidic, basic, or neutral. Continuing down to our second one, we're going to do the same calculation. We're going to look at our OH minus. We're going to take 1 times 10 to the minus 14, which is the KW value. And you always have that number given to you, or not given to you, but you always have it available to you. It would also probably be given to you on an exam. But that's some number you always have. So 1 exponent button minus 14 divided by 2.6 exponent button negative button and 8. And that's going to give you 3.8 times 10 to the minus 7. And again, here we'll put molarity there for our concentration. Also a reminder that your calculator may not give you all the answers in scientific notation. It may give it to you in decimal form, and you might want to convert it to scientific notation. In this case, we want to compare. So our H plus is to the minus 8. Our OH minus is to the minus 7. So in this case, actually the OH minus is larger. The base part is larger than the acid part. And that means that this solution would be basic in this case. Continuing down, same calculation, even though we're given the OH minus is going to be H plus is 1 times 10 to the minus 14 divided by the one they gave us, which is 6.2 times 10 to the minus 9. And we put that in again using our exponent button. we get 1.6 to the minus 6. So this looks like 1.6 times 10 to the minus 6 molar. And now we want to compare. So minus 6 for our H plus, minus 9 for our OH minus. So in this case, our H plus is larger than our OH minus, which means our acid part is larger than the basic part, and it would be acidic. And lastly here, again, same calculation, H plus 1 times 10 to the minus 14 divided by 8.1 times 10 to the minus 3. Going to give us 1.2 to the minus 12. Again, molar because it's a concentration. And in comparisons, in this case, what we see is actually the H plus concentration is less than the OH minus concentration. That basically means that the base part is larger than the acidic part, and that would make this last guy here basic. Any questions on any of those calculations, how we figured out acidic, basic, or neutral? A reminder, if you're seeing yourself sort of having the front part of the number, like for example, this part, and this part looks good, but when you get to the exponent part, it's like off. That usually, again, is an indication that you're not using your exponent button correctly. Again, a reminder that when you do use that exponent button, that EE button or EXP button, you shouldn't hit anything like the multiplication button when you're doing it. You shouldn't use anything like inverse log or anything like that. And also a reminder that if you happen to have some of those newer style calculators that have an actual times 10 to the n button, typically on those calculators, you do need to put parentheses around each of the numbers when you put them into the calculator. Again, for example, if you're going to do the top calculation, you would have to kind of put parentheses around this number and then put parentheses around the next number. Otherwise, the calculator does some weird math. So if you have kind of this is your exponent button that looks like the guy up here, again, you sometimes need to put parentheses around all the numbers. If you typically have an EE button or an EXP button, you don't usually have to worry about parentheses or anything like that. But again, some of the newer calculators, they have kind of like a times 10 to the n or 10 to the x or something like that button for their exponent button. And the way they're programmed is if you really don't put parentheses around every individual number, it will sometimes do weird math. Any questions on that? All right, so why don't you try this one? Forget about which one's greater. Why don't you just calculate the OH minus concentration here? All right, so again, same calculation. We are given the H plus, so our OH minus, not E, OH minus, it's going to be 1 times 10 to the minus 14 divided by our 2.8 times 10 to the minus 5. Again, if you're going to punch this in sort of into your calculator, you would hit 1, your exponent button, your negative button, and 14, you would hit your divide button, and your 2.8, again, your exponent button, and your negative button, and 5. And again, if you kind of punch it in like that, you should end up with, hopefully, 3.6 to the minus 10. Again, here, this would be molar because it is a concentration. And if we wanted to know if this is acidic, basic, or neutral, our H plus was 2.8 times 10 to the minus 5. Our OH minus is 10 to the minus 10. In this case, our H plus is larger than our OH minus, and this would be a acidic solution. Any questions on that calculation there? Our KW, or how to calculate the H plus or OH minus concentration. Obviously, you need to be able to calculate both. And again, I guess the good news is it is the same calculation. So most people have trouble with those two things, really, actually punching it into their calculator correctly using their exponent. And secondly, when they go to compare, they always kind of ignore the negative part of that. So when you have a negative exponent, as we've seen, a negative exponent, the smaller number is actually the larger number. So the minus 5 is smaller in terms of 5 versus 10, but it's actually a bigger number when we look at it. All right, we're going to skip this last one here, and then we're going to go to now talk about the pH scale. So the pH scale basically is a measure of acidity, and the pH scale runs from 0 to 7 to 14, and below 7 to 0, it's acidic. Above 7 to 14, it's basic. And technically speaking, right there, dead on 7, is neutral. And we'll talk about why that is in just a second. We actually already talked about it, but we'll kind of reiterate it in just a second. But for us, we're going to go with that just to make it simple. It's 7 is neutral. If it's slightly above 7, then it's basic. If it's slightly less than 7, it's going to be acidic, slightly acidic, or slightly basic. 7 is sort of our mid-range. As you go towards 14, you become more basic. As you go towards 0, you become more acidic. So there's a lot of stuff on the screen, but really the most important thing here is this. This is the pH formula. The pH is equal to minus the log of the H plus concentration. And the name actually tells you what you need. pH means you need the H plus concentration. And much like everything else that we've seen so far, you will also see this equation written, pH equals minus the log of the H3O plus. And again, H3O plus and H plus, same deal, same thing basically. So again, I'll use H plus, but you will also sometimes see it H3O plus, which is the same thing. And basically when we look at this equation or this formula and the rest of the ones that we'll see here in this chapter, essentially, depending on the calculator that you have, so we'll talk a little bit about calculators here, as to how you'll put it in. So if you have a display calculator, basically you enter it exactly the way it's written. So you would use your negative button, not your subtract. You would hit the log button, and then you would put the number in using your exponent button, probably. Yeah. Now, if you have a non-display calculator, this formula and all the rest of them, you need to actually work backwards, which means you would actually start with the number or the concentration using your exponent button. You then would hit the log button, and then you would hit the negative button. Yeah. So display, you basically do this formula and the rest of them just the way they're written. Non-display calculator, you go backwards, start with the number and work your way backwards. If you're not sure what type of calculator you have, a very easy way to do that is to just hit the log button, the LOG button. If your calculator says log, congratulations, you have a display calculator. If your calculator says error, congratulations, you have a non-display calculator. So if you hit the log button, basically you can determine which one you have, and again, the way you should enter these guys in. So let's talk about everybody's favorite thing, which is significant figures and actually pH or values like pH. The number of decimal places that you would put in your pH value will equal the number of significant figures in the concentration value. So again, what that means is when you get your pH value, the number of decimal places you should take it to is how many significant figures the concentration had. So why don't we try one, just A, to make sure your calculator works, and B, so you can figure out sort of the correct way of displaying a pH value. So if you're given the H plus concentration of 1 times 10 to the minus 5, take a second here, calculate the pH, and then once you've calculated the pH, think about the correct way in terms of significant figures as to how you should write it. So take a minute here, and then we'll talk about it. Okay, so if we calculate this, again, we're going to use the pH equation, and that is our formula. If I can find where I'm going to write, where am I writing? There it is. So the pH is equal to minus the log of the H plus concentration, and that's going to be minus the log of 1 times 10 to the minus 5. And again, if you have a display calculator, you hit the negative, you hit the log, you hit the 1, the exponent button, the negative button, and the 5. If you have a non-display calculator, you hit 1, exponent button, negative button, 5, and then the log button, and then the negative button again. And if you do all that, you will get 5 displayed on your calculator, hopefully. So that's the first part of it. So hopefully you got 5. Now the question becomes, what should you report the answer? Should it be 5? Should it be 5.0? Should it be 5.00? Should it be 5.000000000? I'm going to go no on that last one. It just feels like a lot of zeros, to be honest with you. So let's talk about, again, what the sort of rule is. So the number of decimal places in your pH will equal the number of significant figures in your concentration value. So my concentration value is here. This has 2 significant figures, which means that my answer should have 2 decimal places, not significant figures. So the correct answer here is 5.00. So again, we're not going significant figures to significant figures. We're going significant figures, and the concentration gives us 2 decimal places in our answer, and it would be a pH of 5.00, which also tells us that it is an acidic solution because a pH of 5.00 is less than 7 and thus would be acidic. Question on that. So sometimes people think sig figs is sig figs, but here we're going from sig figs to decimal places. And later in this chapter, we'll talk about going the opposite way from pH back to concentration. So when we go the opposite way, we go from decimal places to significant figures. Any questions on that? All right, let's try a couple here. So we're looking for the pH of each of these. And after you calculate the pH, figure out, is each of these solutions acidic, basic, or neutral? So take a moment here and see what you come up with, and then we'll talk about it. Okay, so let us take a look. So we're looking for the pH. So a reminder that the pH is equal to minus the log of the H plus concentration. So for number one there, the pH would equal minus the log of 2.1 times 10 to the minus 5. Again, we want to make sure that we do put our numbers in and our formula in correctly using our exponent button. And if you do that correctly, you will end up with 4.677778 and some more numbers. Now, in terms of the answer, when we look at our original number here, that is two significant figures, which means we should actually go to two decimal places. So we should end up at 4.68 in terms of our pH. Now, pH of 4.68 is less than 7, which means this solution is acidic, although it didn't ask for that. Any questions on that calculation? That's number one. Now, number two, if we look at it, we want to calculate the pH, which is minus the log of the H plus concentration. And that's kind of important because if we look here, we are not given the H plus concentration. So if you went directly into that equation, you did not calculate the pH. So really before we could do that, we could use Kw, and the H plus concentration would equal 1 times 10 to the minus 14 divided by 5.9 times 10 to the minus 8. And that is going to get us will give us 1.7 times 10 to the minus 7 molar. And now that we have the H plus concentration, we could take the pH is equal to minus the log of 1.7 times 10 to the minus 7. and gives us a pH of 6.77. And that is going to also be acidic. Now, if you happen to have got this number when you did it, 7.23, again, because you used the OH minus, you didn't actually calculate the pH. The good news is you did calculate something. And the good news is you used the OH minus, and what you calculated was not the pH, but you calculated what is known as the pOH. And the pOH is minus the log of the OH minus concentration. And that is exactly what you calculated here, actually. And the nice thing about actually pH and pOH is if you add them together, they equal 14, which means technically what you calculated, you're only a couple slides ahead, what you calculated is useful. So if you did the calculation without realizing that you were calculating the pOH by putting that number in, giving you your 7.23, you then could use this relationship here to get to the pH. You can see that you can get to actually the pH, and it's actually a kind of a convenient sort of calculation because it allows you, as you can see, not to have to use kW. You can use kW just like we did, but now that you know the other equation, you can actually calculate the pOH and subtract 14, which sometimes in a lot of calculations or stuff that you do is a little bit easier, a little quicker. So this equation here, and this equation here are three really important equations in terms of calculating pH, pOH for a particular solution. One last cautionary tale here before we wrap it up here for today's lecture is because now that you see that you can calculate the pH or the pOH, when you're trying to determine if the solution is acidic, basic, or neutral, you should always look at the pH. And what that means is most people in their head have the pH scale, and that's that 0 to 14 scale. The pOH scale actually runs opposite. And so when you have those two values, so for example, if you had both of these values, you calculated this value and then the pOH value, you only want to look at the pH value because, again, that's what most people have in their head is the pH scale, not the pOH scale. And this is the case actually where I was talking about earlier that people will sometimes give, oh, it's acidic and basic because they'll go, oh, the pH is less than 7, it's acidic. Oh, but the pOH is above 7, it's basic. And they'll sometimes give both answers for that question. So again, especially with pH, pOH, there is only one answer. It's either acidic, basic, or neutral. And, that's typically where people will sometimes give multiple answers for that question. Any questions on that or anything we talked about here today? So we're almost nearing the end of this chapter. So we're towards the middle to endish of this chapter. We should be able to wrap it up on Wednesday. A reminder that on Wednesday, we are also having a quiz. So we're going to kind of do it like we did last time. We'll lecture at the beginning. We'll stop probably maybe about 8:30ish. And then you can use that time to take the quiz. And again, the quiz will be on, I believe, chapter 7 is what I said. And if I'm not mistaken, that should be your gas laws and some specific heat that's in that chapter. Also a reminder, as we talked about last week as well, exam 3, I think it is, will be a week from Wednesday, and it will cover through this chapter, so that should be good. We should hopefully be able to finish this chapter here on Wednesday, and then that'll give you a week, and we'll take that exam at that point. So any questions on any of that stuff? Okay, other than that, then I will see you Wednesday. And a reminder again, we're going to lecture a little bit and we'll stop early and then you can go take the quiz. Other than that, have a good rest of your day. We'll see you on Wednesday. Thank you, you too.